Imagine you are out in the woods, right? Like on a freezing cold night, and you're standing right next to a roaring campfire.
Oh, yeah. Best feeling.
Right. You can feel that intense heat radiating against your face. But now, imagine you start walking away from that fire, just stepping backward into the dark woods.
Okay.
Logically, I mean, everyday physics dictates you should get colder.
Right, yeah.
But instead, with every step you take away from the flames, the air around you actually gets hotter.
Wait, hotter?
Yeah. You step 10 feet back, and it's like walking into a pizza oven. You step 100 feet back, and the air is suddenly like scorching at millions of degrees.
I mean, that sounds like a complete breakdown of thermodynamics.
Exactly.
Because the second law tells us that heat should dissipate as it spreads out from a source, right? The further you get from the stove, the cooler the kitchen is supposed to be.
But if you look up at the sky, that exact glitch in physics is happening every single second.
Oh, wow.
The visible surface of our sun, the photosphere, is a blistering but, somewhat comprehensible 5,800 Kelvin.
Which is hot, but...
Right, but if you travel away from that heat source up into the sun's upper atmosphere, that wispy region we call the corona, the temperature just absolutely spikes.
Yeah, we were talking about 1 to 3 million degrees Kelvin.
It is an astronomical paradox. How can a star's atmosphere be vastly, exponentially hotter than the actual surface boiling right below it?
It's crazy.
So, okay, let's unpack this. Because today in this deep dive, we are getting into one of the most stubborn and, frankly, mind-bending mysteries in astrophysics.
It is a phenomenal mystery, honestly. In the scientific community, this is famously known as the coronal heating problem.
Right.
And astrophysicists have been wrestling with this since, gosh, the late 1930s.
Easy. That long.
Yeah, that's when we first realized just how hot the corona actually was during solar eclipses.
Wow.
And our mission for this deep dive is to explore a stack of 4 recent, really groundbreaking research papers published between 2024 and 2026. Because together, they suggest that the answer to this massive star-sized problem has actually been hiding in motions so microscopic that our instruments couldn't even see them until very recently.
It's wild.
So we're going to zoom in on the sun, closer than human beings have ever looked before, to discover this hidden world of magnetic chaos.
I love that. And if we are going to do the cinematic zoom in, we need like one heck of a camera lens, right?
Oh, absolutely.
We are talking about the Daniel K. Inouye Solar Telescope, or DCAST.
Yes.
This is a massive 4-meter class telescope sitting near the summit of Haleakala in Hawaii, and it is a total marvel of modern engineering.
It really is.
It's giving us these unprecedented high-resolution views of the solar surface. And according to this 2025 paper by Kuridze and his colleagues, they pointed this absolute beast of a telescope at the sun and spotted something incredibly strange.
Yeah, they saw these tiny striated structures.
Right. Basically mysterious little stripes or wrinkles sitting right at the edges of solar granules. And when I say tiny, I mean they are only about 20 to 50 kilometers wide.
Which is an astonishingly small scale to resolve.
Yeah.
I mean, the sun is 1.4 million kilometers wide.
Yeah, you could fit over 1 million Earths inside of it.
Exactly.
So naturally, my instinct as an observer is to push back on this a little bit. It's like looking at a massive hot air balloon and noticing a microscopic wrinkle in the fabric,
Sure.
Why do we care about a 20-kilometer wrinkle on a star that size? My first thought would be that these are just optical illusions or like pixel artifacts from the telescope sensor, right?
Right, and that is the natural skeptical response.
Yeah.
But what's fascinating here is that the data proves otherwise.
Okay.
These are not artifacts. They actually trace incredibly fine variations in the sun's magnetic structure.
Huh.
To understand why a 20-kilometer wrinkle matters, we have to look at the physical topography of the sun, because it isn't a smooth billiard ball.
Right. It's boiling.
Exactly, it's boiling. You have these convection cells, called granules, where hot plasma bubbles up from the interior, cools, and then sinks back down at the edges.
Got it.
The edges between these bubbling cells are called intergranular lanes. And that is where the magnetic fields get swept up and concentrated.
Oh, because the plasma is literally like pushing the magnetic fields out of the way as it bubbles?
You are on the exact right track. But the magnetic field pushes back.
Okay.
Because magnetic fields exert physical pressure. So when you have an intense concentration of magnetic flux squeezed into one of those lanes, that magnetic pressure is so strong, it actually displaces the surrounding solar plasma.
Wait, really?
Yeah, it creates a physical dip or a structural depression in the visible surface of the star. It's called a Wilson depression.
A Wilson depression.
Right. You are literally looking slightly deeper into the sun at that specific spot.
So these 20-kilometer wrinkles the telescope saw, they're basically deep, incredibly narrow magnetic valleys.
That is a great way to visualize it.
Yeah.
And Kuridze's 2025 paper used these high-resolution simulations to back up the telescope data, confirming that these tiny visual stripes correspond to extreme, fine-scale variations in the magnetic field.
Oh.
They found Wilson depressions that are as incredibly narrow as 10 kilometers.
That's tiny.
It is. It proves that the magnetic field of the surface of the sun is highly fragmented and fiercely complex on a microscopic scale. It's this jagged landscape of dense magnetic flux tubes.
Okay, so I'm with you on the landscape. We have these super high-resolution magnetic valleys, but, and here's my issue, having a jagged landscape doesn't explain the campfire paradox we started with.
Right.
A static mountain range doesn't generate heat on its own.
No, it doesn't.
To get 1,000,000 degrees of heat up into the corona, something has to be actively moving and transferring energy.
And that logical leap brings us directly to the second paper. This is a 2026 paper published in the journal Nature by Kuridze, Vager, and their colleagues.
Okay.
Because it turns out those tiny valleys aren't static at all.
Yeah, and here's where it gets really interesting. Because Dickist pushed its absolute limits down to roughly a 19-kilometer resolution.
Unbelievable resolution.
Yeah, and at that microscopic scale, those rigid stripes suddenly come alive, they are moving. The researchers discovered that these magnetic boundaries are covered in ubiquitous vortex-like strictures.
Yes.
In fluid dynamics, they call them Kelvin-Helmholtz instabilities, or KHIs.
Right.
And for you listening, if you want to picture a Kelvin-Helmholtz instability, just think about a strong wind rolling over the surface of a lake, whipping up the water into whitecaps.
That's a perfect analogy.
Or like if you look up at the sky and see those beautiful, continuous wave-like clouds that look like ocean surf.
Yeah, those are so cool.
That happens when two fluid layers like cold air and warm air are moving right past each other at totally different speeds. The friction or the shear between them creates these rolling, swirling vortices.
Now, that fluid dynamics analogy works perfectly for neutral gases on Earth, like our atmosphere. But we need to add the solar twist here, which completely changes the physics.
Because we're not dealing with air.
Exactly. On the sun, we are not dealing with regular gas, we're dealing with plasma.
Right.
It's a superheated state of matter where electrons are ripped from their atoms, making it highly electrically conductive. And because it's conductive, the plasma is physically tied to the sun's intense magnetic fields.
Oh, I see. So the plasma can't just flow smoothly past a magnetic field line like wind over a mountain. It interacts with it.
It drags it.
Wow.
The continuous boiling convective flow of the sun's plasma crashes against those rigid vertical magnetic boundaries we talked about earlier.
Okay.
So the plasma wants to move sideways, but the magnetic field wants to stand straight up.
Right, right.
That severe disagreement creates massive shear, the boundary becomes unstable, and the plasma rolls up into these Kelvin-Helmholtz vortices.
So we are literally watching the birth of tiny solar tornadoes just spinning right on the surface.
Tornadoes is a really great mental image. But keep in mind, these tornadoes are made of electrified gas, threaded with magnetic force.
Right. Not your average Kansas tornado.
Definitely not. These vortices occur on scales of tens to hundreds of kilometers, and they are incredibly violent. They mix the highly magnetized plasma with the unmagnetized plasma.
Okay.
They stir up the magnetic fields, creating what physicists call massive turbulent diffusivity.
Turbulent diffusivity. Okay, let's break that down. Is that basically like taking a blender to the magnetic field, chopping it up into smaller and smaller scales?
That is a very accurate way to put it, yeah.
Mm-hmm.
By chopping the magnetic field into finer and finer scales, you drastically increase the surface area where different magnetic field lines interact.
Makes sense.
This makes it a mechanism perfectly suited to transport mass, momentum, and crucially, for our mystery magnetic flux.
Okay, so we found tiny tornadoes chopping up magnetic fields.
Yeah.
Which is a fantastic headline, honestly. But we have to look at the sheer scale of the problem we are trying to solve here. We are trying to heat the entire solar corona, a volume vastly larger than the sun itself, to millions of degrees.
It's a huge energy budget.
Right. And I look at a bunch of 19-kilometer swirls on a 1.4 million kilometer star, and it feels like, I don't know, trying to boil the ocean using a hairdryer.
That's a very fair point.
So what does this all mean? Do these microscopic motions actually have the sheer muscle to move that much energy upward?
It is the ultimate question of scale. Can the microscopic truly dictate the macroscopic?
Right.
because we can't directly fly a probe down to the surface and stick a thermometer into these tiny swirls to measure their energy output.
Sadly, no.
So scientists have to turn to supercomputers. And this brings us to our third piece of evidence.
Okay, let's hear it.
It's a 2025 study by Kuniyoshi, Imada, and Yokoyama. They built a 3D radiative magnetohydrodynamic simulation.
Which is essentially a highly complex digital twin of a slice of the sun.
Exactly.
And simulating that is notoriously difficult, right? Because the density of the plasma at the surface is so much thicker than the incredibly thin ghost-like plasma up in the corona.
Yes.
So the math to connect those two environments usually just breaks computers.
It is incredibly computationally expensive, yeah. But they managed to model a slice reaching from the bubbling surface all the way up into the corona.
Wow.
Because they wanted to test your exact question.
Yeah.
How much magnetic energy do these small-scale swirling motions actually push upward into the atmosphere?
And the numbers they got from this digital twin are just shocking.
They really are.
Like, when they isolated the effect of these small-scale surface swirls, they found that they can carry roughly half of the total magnetic energy supply upward into the corona. Half. We are talking about astronomical amounts of energy being driven by things we literally couldn't even see a few years ago.
It completely flips our understanding of solar dynamics.
Totally.
We used to think massive continent-sized sunspots and giant flares were doing all the heavy lifting for coronal heating.
Right, but it gets even crazier than that. In their simulation, the corona is heated by these events called nanoflares.
Yeah.
And the model showed that more than 80% of these simulated nanoflares occurred specifically during periods when those small-scale swirls were active at the surface below.
The correlation in the model is just undeniable. The swirls drive the heating.
Let's make sure we can picture a nanoflare, though. Because the word flare makes you think of a giant blockbuster Hollywood explosion, you know, like the ones that cause radio blackouts on Earth.
Right, but it's not that.
No, a nanoflare is actually the opposite. It is not one giant blast. It's countless tiny magnetic snaps happening over and over and over again constantly all across the sun.
Yep.
Each one delivers a small packet of energy. Individually, they are tiny, at least tiny for a star, but collectively they go off like a billion microscopic flashbulbs, dumping immense heat into the atmosphere.
We should probably take a quick moment here to be scientifically careful, though.
Good idea.
Because we are weaving these brilliant papers together, but it is important to clarify to anyone listening that the specific Kelvin-Helmholtz vortices observed by the Dickey's telescope in the 2026 paper and the general swirls simulated in Kuniyoshi's 2025 paper aren't necessarily the exact identical phenomena.
Right, they aren't a perfectly one-to-one mapping in the physics.
No, but they belong to the same broader family. They represent a brand new paradigm in solar physics.
Okay.
What these papers collectively show is that a whole hidden ecosystem of previously unresolved microscopic motions, whether they are KHIs or convective swirls, are acting as kinetic engines.
Right.
Feeding immense magnetic energy from the surface up into the atmosphere.
Okay, so I am following the logic. We have the tiny kinetic motions at the surface, the vortices and the swirls, and we have the result way up in the atmosphere, the immense heat and the nanoflares. But I feel like we are still missing the middle of the puzzle.
The connecting piece.
Yeah. How does twisting a magnetic field at the bottom actually cook the plasma at the top? Moving energy around isn't the same thing as generating friction and heat. What is the exact physical chain reaction connecting a surface swirl to a million-degree nanoflare?
That is the most crucial mechanical question, honestly.
Yeah.
And it is exactly what the fourth paper in our stack addresses.
The Bose et al. 2024 paper.
Yes.
And this paper is brilliant because it tackles the physical mechanism head-on. To visualize how this works, I want you to imagine that the sun's magnetic field lines are like long, flexible strands of hair.
Okay, good visual.
And these strands are anchored firmly into the boiling solar surface, standing straight up into the corona. Now introduce our tiny tornadoes at the roots. As the surface churns and swirls, it constantly grabs the roots of these magnetic hairs and twists them,
Rare.
tangles them. It braids these strands together tighter and tighter, twisting the magnetic flux.
If we connect this to the bigger picture, the Bose paper used a combination of incredible satellite observations, specifically from the IRIS satellite and the HI-C 2.1 sounding rocket, along with their own advanced 3D simulations. They wanted to watch what physically happens to these braided magnetic fields. And they built a very clear chain of events. Step one, as you just described, small-scale kinetic motion at the surface, causes the magnetic field lines to twist and braid.
Like twisting a rubber band until it gets all knotted up on itself.
Yes, exactly. And as those lines get braided, they are forced to cross over one another.
Yeah.
This brings us to step 2.
Okay.
When two magnetic field lines pointing in opposite directions are squeezed together by this braiding motion, the plasma trapped between them gets intensely compressed.
Oh, wow.
This creates a zone of extreme electrical current called a current sheet. And we are talking about sheets that are incredibly localized, forming on scales of just a few hundred kilometers.
So you have these massive magnetic forces pushing against each other, building up incredible tension in these highly charged sheets.
Exactly. Which leads to step 3.
Okay, lay it on me.
The tension becomes too great.
Yeah.
The magnetic fields can't hold that twisted, stressed shape forever.
Something's got to give.
Right. They inevitably snap, break apart, and instantly realign into a simpler, lower energy shape.
Yeah.
This violent snapping process is called magnetic reconnection.
Okay, magnetic reconnection.
Yeah.
But, like, when a rubber band snaps, it releases kinetic energy. When a magnetic field on the sun snaps, how does that actually make heat? It doesn't just spontaneously become hot, right?
No, the mechanism is fascinating. When the magnetic field reconnects and snaps to a new shape, it acts like a colossal particle accelerator.
A particle accelerator.
Yes, it whips the plasma particles trapped inside it to near light speed.
Whoa.
These hyperaccelerated electrons and ions shoot out and violently crash into the surrounding denser solar gas.
Oh.
And that immense kinetic collision, that friction on an atomic scale, is what generates the sudden spike of million-degree heat. That is your nanoflare.
That is unbelievable. So let me get this straight. The kinetic energy of the swirl twists the magnetic field.
Yeah.
The magnetic field stores the energy like a spring. The spring snaps, accelerates the particles, and the particles crash to create the heat.
You've got it perfectly.
That is so cool.
And what the Bose paper proved so beautifully is that this dissipation, this particle crashing, heats the plasma in the lower atmosphere, the chromosphere, the upper atmosphere, the corona simultaneously.
Wow.
It perfectly explains why the satellite data showed such a tight, undeniable correlation between heating events at completely different altitude layers. The braiding mechanism ties it all together, carrying the energy from the root all the way to the tip before it snaps.
It is just an epic journey of scale. I mean, let's recap this because it is wild.
Let's do it.
We started looking at the sun and wondering why the atmosphere is millions of degrees hotter than the surface.
Right.
We zoomed in with the most powerful telescope on Earth and found mysterious 20-kilometer tiny stripes at the edges of bubbling plasma cells.
Yep.
Then we pushed the resolution even further to see that those stripes are actually Kelvin-Helmholtz instabilities. Plasma vortices acting like wind whipping over an ocean, dragging the magnetic fields with them. Then, the supercomputer simulations told us that these tiny swirling motions pack enough kinetic punch to carry half the sun's total magnetic energy upward.
Which is still just mind-blowing.
Right. And finally, we realized that these tiny tornadoes are constantly braiding the sun's magnetic hair, twisting the field lines until they form current sheets and violently snap, triggering millions of tiny particle-accelerating heating events all over the star.
It is a stunningly elegant physical chain of events. But, this raises an important question about how scientific consensus is built.
How so?
Well, it is crucial to remember that these 4 papers, as groundbreaking as they are, don't unilaterally solve the coronal heating problem forever.
Right. Science is an ongoing process.
Exactly, a process of refinement and debate. We aren't saying case closed, everyone go home, we found the one true mechanism.
Sure.
What these researchers have done is strongly suggest that multiple kinds of tiny magnetic chaos vortices, convective swirls, magnetic braiding, work together in a massive concert to heat the sun's crown. They have pointed a giant neon sign at the microscopic world.
And that leaves me with a thought that I honestly cannot stop pondering.
Oh, yeah.
Yeah, for decades, astrophysicists were looking for giant, planet-sized mechanisms to explain the sun's giant heat problem.
Like massive sunspots, epic solar flares.
Exactly. But the answer seems to be hiding in the absolute smallest possible motions. I mean, DKIST pushed its resolution down to roughly 19 kilometers, and suddenly, an entire hidden ecosystem of magnetic tornadoes appeared.
It's incredible.
It makes you wonder, what on Earth, or rather what on the sun, will we find when telescope engineering advances enough to zoom in to a 5-kilometer resolution?
Or a 1-kilometer resolution.
Right. Have we even reached the bottom of this magnetic rabbit hole yet? Or is there a whole other layer of chaotic kinetic engines waiting to be found?
You know, if the history of astronomy tells us anything, it's that whenever we look closer, the universe always has another layer of surprise waiting for us.
That's so true.
The deeper we go, the more complex and profoundly beautiful the physics becomes.
The campfire gets hotter, and the mysteries just get smaller. Well, if you enjoyed this story and want to join us for more surprising science extracted straight from real research papers, please like the video and subscribe to the channel.